See this question. In a Young's double slit experiment, the bandwidth obtained is 3 mm. Without disturbing other arrangements, imagine that the whole apparatus is immersed in a transparent liquid of refractive index 4/3. The new bandwidth will be dash. So this is a interesting question. We know what is the equation to find the bandwidth. What is that? Beta is equal to lambda into capital D by small d, isn't it? Where lambda is the wavelength of the light used, capital D is the distance between slits and the screen, and small d is the separation between the two slits. So here it is given that without disturbing other arrangements, you are immersing the whole Young's apparatus in another medium. Okay, so we are not going to disturb these two terms, capital D and small d. So we can say that bandwidth is depending only on the wavelength of light used, and bandwidth is directly proportional to wavelength. So this relation says that whatever change occurs in wavelength of light when you are immersing the apparatus into another medium, the same change will be applicable to bandwidth also, isn't it? We know that refractive index of a medium is equal to wavelength of light in air divided by wavelength of light in that medium. So from here we can say that wavelength of light in medium is equal to 1/nth of wavelength of light in air. So definitely bandwidth in that medium will be equal to 1/n times bandwidth in air. So in this question, bandwidth in air is given as 3 mm and refractive index of that medium is given as 4/3. So we can substitute the values. N is 4/3 and bandwidth in air is given as 3 mm. So here the answer will be 9/4, which is 2.25 mm. So answer is option C. So you just keep this equation in mind. That is enough. When you are immersing an Young's apparatus in a medium of refractive index n, then the bandwidth obtained will be 1/n times the bandwidth obtained in air. If you are keeping the other parameters capital D and small d the same. Hope the solution is clear.